Welcome to this explainer. Today, we're diving straight into a totally fascinating astrophysics paper by Shauna Selman and Eric Corpella. We are looking at what might literally be the ultimate alien engineering stress test. We're going to explore the orbital stability of these massive, lightweight mirrors around exoplanets. It's this brilliant piece of research that was actually submitted to the IAU Symposium on Advancing the Search for Technosignatures. And man, it really forces us to completely rethink how advanced civilizations might actually manipulate their entire star systems.
So let's just jump right into this wild thought experiment. I want you to imagine a highly advanced extraterrestrial civilization trying to, manipulate their own planet's environment. Think about it. If you have a world where one side is just plunged into perpetual darkness, or maybe it just deals with incredibly harsh, freezing nights, how do you even fix that? I mean, you can't exactly just build a bigger light bulb, right? You've got to think on a massive planetary scale. You literally have to harness the power of your host star itself.
Which brings us to Section 1, Alien Megastructures, Giant Mirrors. Let's take a look at the proposed solution to this absolutely immense planetary engineering challenge.
To actually solve a problem like this, scientists hypothesize the use of colossal space mirrors placed right into orbit. According to the source material, extraterrestrial civilizations might actually deploy these giant mirrors for two main reasons. On the one hand, they could use them to fundamentally alter a planet's climate, warming up a freezing world by focusing intense, additional solar energy straight down onto its surface. But on the other hand, they might be used specifically to provide illumination to the planet's dark side, basically creating a permanent, ongoing artificial daylight.
Now, what's absolutely fascinating here is the sheer scale we're talking about. The authors Corpella and Salmon had previously analyzed the detectability of a hypothetical fleet of these mirrors. And let me be clear, we are not talking about small satellites here. The mirrors they modeled are a full kilometer by a kilometer in size. I mean, just think about that massive surface area for a second. Yet, they're modeled to weigh an astonishingly light 1,000 kilograms. It's this incredibly massive structure with almost zero mass to it. Basically, it's a giant, ultra-thin sheet of reflective material just floating out there in space.
And that brings us to Section 2, the radiation pressure problem. Because, as you can probably guess, building massive featherweight structures introduces a really huge physical complication.
You see, the crucial point here is that because these mirrors are so incredibly large and so incredibly lightweight, their orbits are totally disrupted by the star's radiation pressure. Right, so out in the vacuum of space, light actually exerts a physical force. When photons from a star hit a surface, they actually push against it. Now, for heavy, dense planets, this push doesn't matter at all. It's entirely negligible. But for an alien megastructure that's a full square kilometer and only weighs 1,000 kilograms, that push becomes a massive, massive problem.
Just think of these alien megastructures kind of like sailboats out on the cosmic ocean. In this scenario, the starlight acts exactly like a relentless wind pushing against a giant solar sail. I mean, because the mirror's entire purpose is to catch and reflect light, it's inherently catching all of that kinetic force as well. So this starlight wind is constantly threatening to just blow the mirrors completely out of their intended, stable orbits around the exoplanet.
Which leads perfectly into Section 3, Simulating Orbital Survival. So how do we actually know if this kind of alien engineering would even work in reality?
Well, to see if these mirrors could survive, researchers Solman and Corpella had to turn to some pretty complex astrophysics. They created a highly specialized simulation package based on the REB N-body simulator. If you're not familiar, this is a super powerful tool used in astrophysics to model the gravitational motions of objects in space. But they added a twist. They incorporated that tricky radiation pressure we just talked about, specifically programming it to direct the starlight towards the planet's center. They were effectively running a digital stress test for this entire hypothetical alien engineering project.
And honestly, this just brilliantly illustrates the true breadth of their experiment. They didn't just test one simple scenario. No, they simulated these initially circular mirror orbits across a massive variety of configurations to really push the limits of this alien tech. I'm talking testing exoplanets located in the habitable zones of 8 different types of main sequence stars. They placed the mirrors at initial orbit sizes ranging from 2 up to 10 planet radii. They even tested 4 different initial orbital orientations, and they toggled the radiation pressure so it could either affect the mirrors all the time or only during the orbital night. They really covered all their bases.
And at every single time step in the simulation, the researchers were rigorously measuring a very specific set of outputs. They tracked the mirror's survival time, which basically just means how long it actually managed to stay in orbit before getting blown away or crashing down. They tracked its precise trajectory, its distance from the planet's center over time, and its velocity relative to the planet. By meticulously gathering all these clues, they could map out exactly when, where, and how these giant structures might end up failing.
Let's move on to the analysis and see how all this builds together. The researchers didn't just collect raw data. They deeply analyzed the trends in orbital stability by looking really closely at the competing forces at play here. Specifically, they related the stability of the orbits to the ratio of radiation pressure versus gravitational acceleration. Think of it like a constant cosmic tug-of-war. You've got gravity pulling the mirror in towards the planet, while radiation pressure from the star is actively pushing it away. They also looked at the ratio of the planet's orbit period compared to the mirror's orbit period just to see how this whole complex dance affects the megastructure's ultimate survival.
Moving to section 4, the hunt for technosignatures. Now, at this point, you might be sitting there wondering, okay, but why does all of this actually matter to us?
Seriously, why does analyzing the survival time of completely hypothetical space mirrors matter to us right now? Well, it's because unstable megastructures leave clues for astronomers. This entire simulation actually helps us figure out exactly what kind of orbital anomalies, strange transit patterns, or even cosmic debris we should be looking for when we scan the cosmos for alien life. If a civilization actually tried to build these things, and the radiation pressure just blew them apart or totally skewed their orbits, all that scattered massive material becomes what we call a technosignature. It's a detectable sign of past or present technology that our modern telescopes might just be able to spot.
Which brings us to the end of our explainer, and man, it leaves us with such a thrilling mystery to ponder. If the raw physics of radiation pressure makes these massive, lightweight megastructures incredibly difficult to maintain in stable orbits, what does that mean for advanced extraterrestrial civilizations out there? Did they somehow find a way to anchor them? Did they just bite the bullet and use heavier, much harder to launch materials? Or did they abandon space mirrors altogether for some other bizarre, spectacular engineering solution that we haven't even dreamed up yet? We don't know for sure, but keep looking up because the clues to alien engineering might literally be hiding right there in the physics of the stars.